All right, so we've seen one type of application for derivatives so far, and that is our particle motion problems. So now we're going into our second type of an application that we're going to be looking at, which are going to be word problems where we're looking at related rates. Kind of the big thing with these type of word problems is there's going to be several types of word problems that we look at in calculus. And knowing what kind of a problem we're looking at is going to be important because your strategies and your methods of solving are going to differ depending on the type of word problem that we're going to look at. So we've already seen the particle motion problems, which are fairly obvious. It'll start with a position function or a velocity function. You'll discuss the acceleration, when does the particle move left and right, and those types of things. What we're going to be looking at is this idea of related rate. It's in chapter 3 because it's an application of implicit differentiation. But I do want to kind of show you, kind of before we actually get into the how that we solve them, to look at what is the key thing that's going to tell us that this is a related rate problem, right? The first thing is that for you to always notice that when you're reading through the problem, and, with all the information that's have, you really need to find the sentence that is going to ask you, what are you being asked to find? And so what you see right here is, as you read through, you're given some information, which we'll come back and talk about, and some given length and width here. And then they're going to ask, how fast is the perimeter changing and how fast is the area changing? The how fast is telling you that you're looking for a rate, aka a derivative. And so the idea here is that it's called a related rate problem because we're going to be given some information about rates and values, and then we're going to find a formula that will relate all of the information we're given together, and our job is to find a rate given information, related rates. That is different than if we're going to take a look at an optimization problem. This is going to come in the end of chapter 4. We're going to need to do quite a bit of applications and work in chapter 4 before we can do optimization. But these are the two classic word problems, and the optimization word problems typically in related rates are going to get confused. The idea, though, is to me it's fairly obvious what we're doing. In an optimization problem, you're always looking for a maximum or a minimum. Like here, we want to find two positive numbers whose sum is 60, and the product of one times the square of the other is a maximum. Notice I'm not looking for a rate. I'm not looking for how fast on something here. I'm looking for a maximum. Another example of an optimization problem. If we look at this one, we're trying to find the dimensions that will produce a rectangle with the maximum area. So I'm looking for a maximum there. If I look at this example, I'm trying to find the largest grazing area. If I look at another example, I'm trying to find the point on the curve closest to, so that's a minimum distance. So an optimization problem, you're trying to find extrema, maxes and mins, whereas in related rate problems, you're trying to find a rate. And so that's going to be the key thing when we're looking at it. So I was just kind of looking ahead. Now, there are some essential skills about related rates that you're going to need, and you already have a lot of these skills. We're just going to organize it. So we know that calculus is the study of change, and that when we start using words about increasing, decreasing, growing, shrinking, we're talking about rates. Remember that our kind of in chapter 3, we would find a derivative, a slope, also known as a instantaneous rate of change, and then you would interpret it as the when something was happening, the what, which way was it going, increasing or decreasing, by how much, what was the actual derivative, and then your units of time. So we're basically working backwards. One, we recognize that a rate of change, how much a quantity changes with respect to time, is a derivative. So we basically are going to identify in these word problems what quantity you're interested in with units, and then you're going to want to determine what rate you are being asked to find. And this rate is always d quantity with respect to time. Now, you need to remember that, paying attention to knowing whether your quantity is going to be increasing or decreasing is important. That positive rates, the quantity increases. Positive rate means that your quantity, whatever it is, kind of like your position function, is increasing. And if you have a negative rate, your quantity is decreasing. Okay, classic information from what we learned in chapter 3. And units are going to be super important in these problems. All right, so now we're going to do like building blocks here. We're going to start with the simplest thing that you're going to need in order to do these problems. One thing is you have to be able to read the word problem and interpret it mathematically. So example 1 here is going to be information that you are given in the problem. So these are going to be rates given in the problem. Okay, so you're going to identify a quantity, you're going to identify a rate that you're looking for, and then they're going to give you information about other rates in the problem. Hence, this is called related rates. And your job is going to be interpreting the sentences, kind of going backwards from what we did before. Our when, what, which way, by how much with units, they're basically giving you this here, and your job is to go backwards and write the rate down. So like, for example, if we see a sentence like Mortimer is growing at a rate of 3 inches per year, your first step is to identify the quantity that you're talking about. The what is changing. So if you look at this, Mortimer's growing, what's changing? His height. So you identify your height as a variable, we name it, and we give units to it. So since it's inches per year, the height is going to be measured in inches. So we figure out the what, and then we look at it and we think to ourselves, well, which way? It's growing, so that's going to be important because that's going to tell us whether our rate is positive or negative. So we know that this rate that we're describing is positive. And since we are doing a rate, we need to name it so that we know what we're talking about. And since the height is changing with respect to time, we're basically being given dh dt because the height is changing with respect to time, your rate of change. So you identify what derivative you know, we identify that it is positive, and then we write down our amount with our units, inches per year. And so essentially what we're doing in this problem is just translating a sentence that you're given in a word problem by identifying the quantity, whether it's growing or decreasing, so make sure you know whether the rate is positive or negative, and then identifying it using derivative notation that the rate of change in height with respect to time is dh dt, because this is going to be information we're going to use to actually solve the problems that we have. So when you look at your second example, and let's go ahead, and this is our rate, aka our derivative rate of change. There. All right, so we'll go to the second one. Your stock portfolio is losing 5 cents per day. All right, what is losing 5 cents per day? Your portfolio. It doesn't really matter what you call it. It's the money in your portfolio. You just have to identify a variable. So let's call this M for money, and we'll just say amount of money in your portfolio. The units, since they're saying losing 5 cents per day, I'm going to initially, let's start this with cents as our units. We'll come back and talk about this in a second. So my quantity, my what, is my money in the portfolio. All right, and then my change, my rate of change that they're giving me, it's losing 5 cents per day. So right there, that's telling me that this is a negative rate. So when we take a look at this, our dm dt, our actual rate of change, is going to be negative 5 cents per day. Okay. Now, units are one of those things where you can change your units however you wish. You just need to make sure that you have consistency in your units. If we wanted to, we could come back in this problem and say, I don't want to measure my amount of money in cents. It doesn't make any sense to me. Haha, very funny. But maybe I want to measure it in dollars. But if I'm going to measure it in dollars, that would mean over here, when I do my dm dt, that I need to do negative 0.05 dollars per day. You just have to have matching units as you're doing it and convert your values to make sense in terms of the problem. All right, in the next example, your radius gets larger by 4 feet each hour. So what quantity is changing? The radius. What units are we measuring it in? We're measuring it in feet. Our rate of change, dr dt, is going to be getting larger. Okay, so we identify the larger part. So we know we have a positive rate. So our value, dr dt, is going to be positive for feet per hour. Right? The outside temperature is dropping by 5 degrees Fahrenheit per minute. The what, your temperature, I'm going to use capital T for temperature. Say outside temperature, degrees Fahrenheit. And then our rate, dt, make sure you use capital T, lowercase t. The rate of change, it's dropping by 5 degrees per minute, so that's a negative rate. So our rate of change that we're looking at would be negative 5 degrees Fahrenheit per minute. All right? So skill number 1, you're going to have to read through the problem and you will be given rates that you are going to use to solve the problem. So you would interpret all of your sentences that have this by writing them with a quantity, identifying a variable, and identifying your rate by using your derivative notation. Now, the second skill set that we have in this application problem is implicit differentiation, because we are pretty much always going to be taking the derivative of your variables, whatever they are, with respect to time, because we're looking at this rate of change over time. And so it's not 100% that, but majority of the time it's with respect to time. So when we take a look at this, when we take the derivative of x, it's not going to be 1 anymore because I'm not taking the derivative of x with respect to x. What we're doing is taking the derivative of x with respect to t. So this would be dx dt, that we have to remember the whole chain rule process that's going to be involved. If I want to take the derivative of w squared, it would be 2w dw dt, that you are following it with that chain rule because of the implicit differentiation, because you're taking the derivative of a quantity with respect to another variable time. So you want to pay attention to that. You are thinking of your w as a function of time, that if this was width is changing as time changes. So your width is a variable and you're taking the derivative with respect to time. And when you see something like this, it's like, hey, make sure you use product rule. So I would do my first L times the derivative of W with respect to T plus your second W times the derivative of the first L with respect to T. So you just need to have a skill of taking your derivative using implicit differentiation. All right, so let's take a look at an actual problem. So here we have the problem. We've identified that this is a related rate problem because what they're asking me, when you read through your problem, let's look at what we have. We're given a information here, which is a rate. You're given information here, the width is increasing by 3 feet per second. So here's another rate. Then they give you some information about the length. Now I'm going to talk about this in more detail in a second. But I'm going to tell you that this is your when you're interested in what's going on. And then we have the question, which is saying, I want to determine how fast the perimeter is changing. Let's do A first. So we're looking for a rate. So I immediately kind of read through this and go, hey, this is a related rates problem. I'm given some rates and a when, and then I'm asked how fast. So I'm being asked to find how fast. So in your head, you're going to make a variable. You're going to set your quantity, a variable, what you're looking for. We're looking at how fast the perimeter is changing. So I'm going to do P perimeter. And then the units, I'm going to look through my problem and see that the other rates that I'm given are in inches. And they all match. So I'm going to go inches for my perimeter. And then what I'm being asked to find is I'm trying to find a rate, how fast the perimeter is changing. So I'm trying to find dp dt. So I kind of identify that part. All right, and then we go to what are we given? So we read through the problem again, and now we're going to look at what rates and what information were we given. We take the first sentence, the length of a rectangle is decreasing by 2 inches per second. So we create a variable, length. We're measuring it in inches. And then we identify the rate that we are given, dl dt, it's decreasing, negative 2 inches per second. So we write that down. We are also given a rate about width. So we identify a variable, a quantity, we name it, we give it units, and then we write the rate down that we're given. dw dt is increasing, positive 3 inches per second. And then they also gave me a when. I like to call this the snapshot. And I'm going to talk about this in just a second before I answer the next question. But the when snapshot, when are we interested in finding out how fast, is when the length is 10 inches and the width is 6 inches. Okay, so when you're doing this, let's put this in a box. This is going to be very important. Now, typically in a lot of these problems, you are going to want to draw a picture. And there is going to be the temptation when you start drawing your picture to put this when information on your picture. But this should not go on your picture because it will confuse you. What you want to look at is determining what are your variables in the problem. What is changing over time? All right, so what we have is this rectangle. So here's just a generic rectangle. I actually do not know what the length and the width of this rectangle is because over time, the length and width of this rectangle is changing because they gave me the rate at which they are changing per time. So when you take a look at this, each second, if you look, let's go 1 second later in time. Here's my original rectangle at some instant in time. I don't know when, and I don't know what my length and my width are. The next second, it looks like this. What happened? My length got smaller and my width got larger because of the rates that they gave me. If I go 1 more second, the length got smaller, the width got larger. Go 1 more second. And so each time we do this, we see that our rectangle is changing with respect to time. So when we draw our first initial picture of this, and I'm identifying my variables in the problem, I'm thinking about the fact that in this rectangle, do not put 10 and 6. Don't do that because that's an instant in time. I'm talking about through the whole problem, I want to recognize that my length and my width are changing over time. And as my length and width are changing, that's causing my perimeter to change. So my variables in the problem are L, W, and P. The variables of the units, quantities I was given information about their rates of change, the quantity that I'm interested in finding the rate of change for. So you always list your variables first. And then you go, well, now, what would be the rates that I'm going to be eventually relating? The rate for the length, dl dt, the rate for the width, dw dt, and the rate for the perimeter, dp dt. And with these problems, what you are basically going to do is 2 steps. You are first going to write a formula that relates your variables. And this is why I'm not even using the snapshot, the when. That will come at the end of this problem. You first figure out what varies, what are your variables, and then you're going to write a formula relating your variables. And this is length, width, and perimeter, so we know that perimeter is 2L plus 2W. Okay, so we write that formula first. This is going to be our quantity equation. Once you get your quantity equation relating all your quantities, okay, then you're going to take the derivative of your quantity equation, and we're going to do that implicitly, the derivative of P with respect to T. We're going to take the derivative of 2L plus 2W with respect to T, and again, you have to show this step because so we can see what we're taking the derivative with respect to. And when I take the derivative of p with respect to t, it becomes dp dt equals 2 dl dt plus 2 dw dt. So that's my implicit skill of taking the derivative. This is the formula that is our target in the word problem because this is my related rates formula. This is the formula that relates the rates together. And so now I'm going to use the given information. So here's where you would finally use a snapshot. You may not use it. What I know from what I'm given is that L is 10, W is 6. We know dL dt was -2. And we know dW dt was 3. So this is all the information that you were given. Here's the when. Here's all the speeds that you were given. Right? And we're trying to find dP dt. So if you look in your formula up here, here's what you're looking for. And you have a formula. You need to plug in the items you're missing, which you have listed from your information above. So dP dt would be 2 times -2 plus 2 times 3. It's a plug and chug at this point. You plug in all the information you know, and then you're like, oh, here we go. This would be -4 plus 6, or 2. Our units would be inches per second. And then we take the rate that we have found and we answer using our sentence, the when, the what, the how, much, which way, and units. So we have our when the length was 10 inches and the width was 6 inches. At that moment in time, the perimeter, the what, is positive rate increasing at 2 inches per second. And there's our answer to the question. Now, you might wonder in this one, I didn't even use the 10 and the 6, I didn't even plug them in. Well, that was because the perimeter must be increasing at the same rate for the entire problem. It doesn't depend on what your current length and width is because your formula for dP dt did not depend on L and W. All right, let's look at part B in this. In part B, we were asked to figure out how fast the area is changing. All right, so let's do A. So our units would then be inches squared. So we're trying to find dA dt. All right. The information that we're given is the same. dL dt was your -2 inches per second. Your dW dt was 3 inches per second. Now the only difference here, in our instant, our when, L equals 10, W equals 6. Okay, so we have the same given information. Our variables, now we're trying to take our rectangle. Again, we have our length and our width, but we're trying to relate it to our quantity area. So our variables are area, length, and width. Our rates are dA dt, dL dt, and dW dt. So now when I first write my formula relating my variables, relating the quantities, I'm going to use area equals length times width. I'm going to take the derivative of my quantity formula implicitly with respect to time. So I show that I'm taking the derivative with respect to time. You will, we did this on the first page as one of those skills. We would have L dW dt plus W dL dt and dA dt. So here is my target formula, my related rates formula. Now notice that in this related rates formula, here's what I'm trying to find. Notice that this time this rate depends on the rates of how fast the width and the length are changing, and it depends on the L and the W. So that's where that given snapshot is going to come into play, that the area is not changing at a constant rate of change throughout the life of the problem. The area depends on what you are currently sitting at. So your given information, your when, your L is 10, your W is 6, your LDT was negative 3, and your dW dt, I think I have that backwards. The LDT was negative 2. Negative 2 and 3. So now when I plug and chug into my formula, I actually do need all of them. So 10, negative, positive 3, plus W, 6, times dL dt, which is negative 2, which gives me my rate of change in area is 30 minus 12, which is my 18. So, and then we finalize and answer the question, okay, when L is 10 inches and width is 6 inches, the area is positive, increasing at 18 inches squared per second. Okay, so make sure you have your units correct, and then you're done with the problem. So that was a nice quick intro to your related rates.